On May 7, 1981, influential physicist Richard Feynman gave a keynote speech at Caltech where he was a professor. Feynman opened his talk by politely rejecting the very notion of a keynote speech, instead saying that he had his own ideas on what to discuss and that everyone should speak on what they please. And for Feynman, this meant proposing a whole new technology that could simulate physics with computers. He called this new tech quantum computers, which could simulate quantum systems, like the tiny worlds of atomic and subatomic particles, including electrons, worlds far too difficult for classical computers to process. He capped the talk by saying, quote, "Nature isn't classical, damn it, and if you want to make a simulation of nature, you better make it quantum mechanical. And by golly, it's a wonderful problem, because it doesn't look so easy." That lecture 44 years ago is widely considered to have kicked off the field of quantum computing. Welcome to Tiny Matters, a science podcast about the little things that have a big impact on our society, past and present. I'm Sam Jones, and I'm joined by my co-host, Deboki Chakravarti.
Today, we're diving into the world of quantum computing, its big challenges and exciting potential applications, such as decoding tough-to-crack encrypted messages or discovering new drugs.
Yeah, it's a fascinating field, but a bit of a heady topic. So we'll do our best to break it down. To start, what is a quantum computer? One way to understand quantum computers is by comparing them to classical computers, like the ones we use every day, or the one that I'm recording this podcast episode on right now.
For example, in a classical computer, the simplest element is a bit, which can be either 0 or 1 and stand for the logical values false and true.
That's Francesco Evangelista, professor of theoretical chemistry at Emory University.
But in a quantum computer, you have a superposition of 0 and 1.
Superposition is a key concept in quantum mechanics, a field of study that describes the behavior of matter and light at very small scales down to the subatomic level. Think electrons. Superposition describes how quantum systems like electrons can exist in a combination of different states until they're observed. So, for example, an electron might emit light when transitioning between energy levels. And it's when you observe that light that you get a defined value.
A good way to think about superposition is to imagine a spinning coin. While it's spinning, the coin is neither heads nor tails until you slam your hand on it. In quantum mechanics, the coin is neither heads nor tails until you observe the properties of a system, which means interacting with the system and essentially getting heads or tails. It is a strange concept.
Yes, it is.
The same way when in chemistry we talk about the electron not having a definite position in space or having both the properties of a wave and a particle. In a quantum computer, you'll have the analogous thing happening for bits.
So instead of having bits like in classical computers, quantum computers have what are called qubits. In theory, the advantages of quantum computing over regular digital computing is that quantum computing can handle enormous possibilities, which could allow them to solve much more complicated questions.
But making quantum computers a reality, as Feynman said, is not so easy.
In my opinion, quantum computing is really just getting started, both in terms of understanding the capabilities of what quantum computers can do from a formal point of view, but also in terms of building actual quantum computers. So today, we have what I would say are prototypes of quantum computers. They are initial experimental realizations, but they're not the real deal. We know that many of the interesting applications of quantum computing really require computers that contain many more qubits than the ones available today.
It's estimated that between 100 to 200 quantum computers exist around the world today. In 2023, a startup in California unveiled a quantum computer with the largest number of qubits to date at 1,180 qubits. But quantum computers that academic scientists have access to have far fewer, around 127 qubits. While that may not seem like many, qubits have exponentially more computing power than the bits in classical computers. Since bits can only represent either a 1 or 0, its computational power increases linearly. Qubits, on the other hand, can represent 1 or 0 at the same time. So its potential computation is 2 to the nth power, with n being the number of qubits.
And the current quantum computers have some serious issues, with accuracy topping the list.
I think that we are used to computers that don't make mistakes, or they make them at such a small rate that it doesn't affect our life. So what's happening in quantum computing, it's a little bit like, for example, when I was a teenager and we used early versions of Windows, and a lot of programs were buggy and our computer would crash and you would have to restart from scratch what you were doing. But nowadays we kind of don't experience that often. Now in a quantum computer, the rate at which the errors happen is very high. And its effect is that as you are manipulating data, you're basically doing a computation. That data gets corrupted. So when you perform a computation and it's too long, eventually that data becomes noisy. And at some point, it's so noisy that you can't extract any useful information.
There's multiple reasons for these errors. The goal is to allow qubits to maintain their states until it's time to observe them. So quantum computers need to be completely isolated from disturbances in the environment, like heat or vibrations, to work properly. That's really hard to do. It's also why quantum computers are kept at extremely cold temperatures close to absolute zero. The error rate also depends a lot on how the quantum computer is made.
On the integrated circuits, I think it was pretty clear what they were going to look like, and then it just became a matter of scaling it up. But in the quantum computing world, I don't think we have the final hardware strategy pinned down.
That's computational biochemist Kenneth Mers, a professor at Cleveland Clinic and Michigan State University. Unlike classical computers, which all use the same types of silicon chips, quantum computers don't all use the same physical system. Some use photonic qubits, which are made of photons of light. Others use so-called trapped ion qubits, which are charged atoms suspended in an electromagnetic field. A popular choice is to use what are called superconducting transmon qubits, which use a material that has no electrical resistance below a certain temperature.
It's like you have this quantum mechanical system that contains a lot of information because of superposition, entanglement, and you could use that potentially for computing. So then the challenge becomes like, how do you assemble a quantum mechanical system that you can control, which would be then your quantum computer? So how do you array your qubits? How do you connect them? And this is what you're seeing in the New York Times, Google and Microsoft and IBM are having these dueling papers coming out. It's all about how they're assembling these quantum computing devices.
Each kind of hardware has its trade-offs, Kenny says. For example, a system using a superconducting transmon is faster, but has a higher error rate, whereas a trapped ion system is slower but has a lower readout error.
The other thing, too, about quantum devices is that on a classical computer, you tend to do the calculation and get a result. Quantum device, you may do what are called many shots. So you may have a problem you're trying to solve, and you do a lot of shots, and then at the end, the answer is by consensus. So if you do 500 shots and 300 give a certain answer, by consensus, that is viewed as the answer. They looked for about a 2/3. So it's not kind of where you do, say, one shot through a classical hardware, you have the answer. So it's a little bit different in terms of the way you do the computing as well.
Despite these high errors and other practical issues, which researchers are working to address, interest in pushing quantum computing forward has only grown over the years.
Kenny says a major turning point for the field happened in the mid-1990s.
But really, I think what launched it, which got the attention of, say, the governments around the world, because China is spending, 10, 20 billion a year now on quantum computing research, US, all these companies are spending lots and lots of money on this, was a guy named Shor. And he came up with this way to factor numbers.
In 1994, researcher Peter Shor published a landmark study. He had developed a quantum algorithm that could break numbers into their prime factors way faster than a classical computer. This had huge implications for cryptography, the secure encoding of sensitive information, something very appealing to governments, for example.
So all of a sudden, it's like, oh my gosh, all our signals, which are encoded by prime numbers or whatever you happen to be using. If we had a device like this, we would completely be able to read everybody's signals.
Not only could you decrypt messages, you could also send them more securely with a quantum computer. Imagine being able to send a message, and if it gets intercepted, you could disturb the signal, essentially erasing the information.
When it comes to applications for quantum computing in other fields, like chemistry, Francesco told us the path is not as clear.
One of the issues that we are still trying to understand is what are the best uses of quantum computers in chemistry. And sometime in a field, you need time to understand what are the good problems for a new technology. So it could be that the problems we're focusing on today might not be the actual problems on which a quantum computer is going to deliver impressive new results. But today, we have to focus on our immediate needs. And so, for example, as a computational chemist, I want to use quantum computers to predict the energy and properties of molecules.
Many researchers have started to explore combining quantum computing with regular computing in hopes of getting the best of both worlds.
So you basically take the strengths of a quantum computer and combine them with those of a classical computer. And when you do this, you can take a calculation that is difficult and you can divide it into an easy and a hard part. Then you let the quantum computer solve the hard part, and the rest can be handled by the classical computer. And so, for example, with this technique, we have come up with ways to calculate the energy of organic molecules. And we even looked at simple organic reactions where, for example, a molecule undergoes a reaction, but with two possible pathways. And we've used quantum computers to calculate the energy differences between these two pathways. And so approaches like this are likely to be the way we're going to realize practical quantum computation that have an impact in chemistry.
And the hybrid approach is bridged by an internet connection. Scientists like Francesco submit their queries remotely to a shared quantum computer used by dozens of scientists. But even coding for a quantum computer looks different than writing code for a normal computer.
They're different in many ways. One of them is the level at which we write code. So when we write computer code for a classical computer, we are basically expressing some logical operation or mathematical operation. But the way we do this, it's typically at a high formal level. So for example, I can say, if this variable is set to 5, do this series of operations. Now, on a quantum computer, we are dealing with more basic operations. They're similar to the low-level operations that are used by classical computers, but they're manipulating a quantum state.
In a classical computer, this is called assembly. It's the basic instructions that a computer processor executes. While quantum computers use some of the same coding language as classical computers, programming for these machines requires a more open-ended and novel approach.
Kenny says that teaching people how to code on a quantum computer may be one of the biggest challenges for the field.
When I was a grad student, they started talking about parallel computing and how of, say, 10,000 programmers, maybe only 1,000 could really code in parallel.
Coding in parallel means breaking a computation into smaller parts and running them simultaneously.
So I think we're at the same thing. Like for me, decades and decades of thinking serially, thinking in terms of classical computing. And now towards the end of my career, I'm being forced to think in this quantum mechanical way. And I think this is where young people starting into the field, they won't have all this baggage. I have decades of baggage that I have to break to think quantum mechanically. So that's why I think education is so important, that we're going to need the new workforce, new people with the talent and skills to think in this really novel way to take full advantage of the power of this technology.
Labs like Francesco's are facing that training challenge head on.
I've seen this problem in first person because I had to start doing quantum computing research in my group, and my students and I had zero experience. And so the way we solved the problem was to actually build a quantum computer emulator. So what an emulator does, it's a piece of software that effectively behaves like a quantum computer, but it runs on a classical computer. And creating an emulator was very important for us to understand the real differences between these two forms of computation. But I think the major issue is really that to start doing quantum computing, you have to know a little bit of computer science, but also quantum mechanics. And I think now you're starting to get into a very broad background that not many students have. So I think we're all asking ourselves, how can we make this more accessible?
Still, quantum computing holds a lot of potential for the field of chemistry. Francesco says it's uniquely good at calculating the energies of reactions that change over time, including photocatalytic reactions, where a catalyst activated by light speeds up the reaction.
On a classical computer, when we're trying to determine the structure of a molecule, its properties, or how it reacts, we have to make approximations. One of them, for example, is the Born-Oppenheimer approximation. And this is just the idea that nuclei are fixed in space and that electrons react instantly to changes in the position of the nuclei. But we know in reality that this is just an approximation and that it breaks down in photochemistry when we consider transitions between different electronic states in nuclei are moving. But we can go beyond this with quantum computers because we can treat both electrons and nuclei quantum mechanically at the same time. And so that's one type of advancement that we couldn't achieve without something like a quantum computer. And what that would enable is to model chemistry more accurately.
Kenny is also optimistic about the potential applications, though he offers a word of caution.
I think we can do things better, faster, if we can discover new materials, new batteries, new drugs, new proteins, better understand the human condition. That's going to be amazing. And these things are going to enable that potentially. And that's another real exciting thing. I mean, the negative of all these, we're human. And unfortunately, humans are very good at converting kind of these things into weapons and things like that. So maybe that's not so positive. But again, I think the benefits far outweigh some of the negatives.
Both Kenny and Francesco suggest that the field as a whole is on a slow burn trajectory. And that could be totally fine.
I think that often when we think about scientists and their work they do, we approach it with the question, what is it useful for today? And science has this balance of short-term and long-term goals. So quantum computing is a field where we're looking at a long-term goal. And in the history of science, we've seen things play out on very long arches of time. Now think about electromagnetism, when it was discovered and when we got computers. Sometimes it's just centuries.
Electromagnetism is the study of how magnetic and electrical fields interact, and it's essential for computer processing, data storage, and even screens. It was discovered in 1820, but the first computer wasn't built until the mid-1940s.
I like to be open to surprises. I think the field of machine learning is an interesting example, where for many decades people knew the fundamental ideas that would eventually lead to breakthroughs, but the engineering behind it or the data needed wasn't there. And in this case, it took a lot of time, a lot of patience, and also a lot of ups and downs where the community was excited about that problem. And then there were these winters where people were less interested in machine learning as a general field. And then eventually you get to a point where things suddenly change and you have a big impact. And it's possible that things will play out in the same way in quantum computing. I definitely fall on the more cautious camp. So I'm not one of those people that would go to say, yeah, in 10 years, this is going to revolutionize chemistry. But I'm open to be surprised by what human ingenuity can do.
I really like that sentiment, being open to being surprised. That's kind of a lot of what science is, I think. You know, there's a lot of waiting, and sometimes the progress is slow, but then all of a sudden you get these life-altering surprises. It seems like quantum computing is a field where surprise could definitely bring about world-altering change. All right, let's tiny show and tell.
Cool.
Let's see. Mine is animal themed.
Mine too.
Oh my gosh, what if we do the same one?
I don't know. I doubt it though.
Okay.
Because mine is like small animals.
Okay, mine is actually big animals.
Great. Okay, we're on different scales. You want to go first?
Sure. So I'm going to give you some rhinoceros news. Scientists at Scripps Research Institute, the San Diego Zoo Wildlife Alliance, and Max Planck Institute for Molecular Genetics, and some other collaborators have mapped the entire genome of a northern white rhino. Why is this exciting? Well, there are only 2 northern white rhinos remaining in the world. Both are living at the Ol Pejeta Conservancy in Kenya. And they're both female, which is a problem when you're thinking about reproduction. So my understanding is that at this point, before this study came out, there are about 30 northern white rhino embryos that are currently being stored, like deep freeze stored, that were created using sperm from 2 now dead males, plus the eggs that have been gathered from one of the females that is still alive. But there have also been northern white rhino stem cells developed that one day scientists are hoping could be used to generate sperm and egg to then make more embryos. But without a reference genome, it's impossible to say whether during their growth in the lab, these stem cells picked up any mutations or issues that could ultimately not lead to viable sperm and egg, or potentially lead to ones that, yes, you get an embryo, but there is some sort of harmful effect. So now that they finally have this full genome sequence, they've been able to analyze the genetics of these stem cells in comparison. And they've actually found that one of the lines that they thought was the most promising has this massive amount of DNA missing, like 30 million base pairs affecting over 200 genes. And some of those genes had really essential roles like tumor suppression and reproduction. And so now they're planning to go back, screen all of the other stem cell lines to make sure essentially they're not setting themselves up for failure. So I thought this was like very cool because I think we talk a lot about, oh, we got a genetic sequence for this or that. And it's like, okay, that's cool. That's neat. Like some of it's comparative where you have that genetic sequence. So you can say, what are some of the genes that are really similar in this fly or bat or, this or that compared to people? And essentially, could we manipulate something in our own genome or in, something like that? But like in this case, it's really this basic idea of if you don't have a control, you don't have any sort of comparison, how are you supposed to know? You don't know you have a mutation if you don't have the quote normal genome.
Yeah.
So I just thought this was really interesting.
Yeah, that is really cool. And you don't think, or at least I don't always think about these really specific problems that come up when we're trying to do stuff that obviously we do in humans, but now we're we're thinking about in other species. It doesn't occur to me oh, right, we need to have this information to be able to do that.
Right. And you think oh yeah, great. We were able to get stem cells. So we're just going to, plug ahead. And it's no. We don't actually know if those are so mutated that nothing would ever work. And so it's how much time and money and whatever else.
Yeah.
And also it could then have really negative implications. I mean, I just said some of the genes relate to tumor suppression. You don't want to set these animals up for failure, even if this is a endangered, almost extinct species, right?
Yeah.
So, I just thought this was very cool.
That is really cool. Well, Sam, I have for you a study that was published in 2024 where researchers reported that they had discovered 9 new tardigrade species and found a lot of other tardigrade species in Denmark. And the important detail to me is that the researchers were around 30,000 Danish school children between the ages of 7 to 16.
Oh, that's so fun.
Obviously, they weren't doing this all on their own. They were working with their teachers, and they were also working with scientists from the National History Museum of Denmark. And this is part of a big citizen science project called Mass Experiment. So these kids, they collected moss and lichen from parks, forests, and other areas, including apparently cemeteries.
Okay.
And that meant that there were a lot of samples. That was really exciting for the tardigrade scientists who were looking at these samples because, collecting thousands and thousands and thousands of samples is a lot for any single person. But this way you could get a lot of coverage and you could also get kids excited. And so when they got the samples back to the researchers, the scientists sorted through them to see what they could find. They found 55 tardigrade species, 14 of which were known in Denmark before. So that was a good chunk that hadn't been seen in Denmark before. And 9 had never been described. It was also exciting because they were able to find quite a few males of the species, and that's kind of unique because a lot of tardigrade species that live on land are actually asexually reproducing females. So it's actually pretty surprising to find males. So yeah, I just really enjoyed it.
I love that. That's so fun. Also, it's that is how kids get into science.
Yeah.
I mean, not always, but a lot of times. I think getting out there and how cool to be when I was 12, I helped discover new species of tardigrades.
I know. I think it's so cool to like realize just how much there is to discover. I remember when I was little, like my parents are scientists, and I remember asking my mom like very earnestly, like, have you discovered anything? And she's like, yeah, of course. And I was like, what? Like, you're just discovering things out here? And now I'm like, oh yeah, it's because like there's so much knowledge.
There's a lot to discover, for sure.
Yeah. Thanks for tuning in to this week's episode of Tiny Matters, a podcast produced by Multitude and brought to you by the American Chemical Society, a nonprofit scientific organization based in Washington, D.C. This week's script was written by Tien Nguyen and edited by me and Michael David, and by Sam, who is also our executive producer. It was fact-checked by Michelle Boucher. Audio editing was done by Jeremy Barr. The Tiny Matters theme and episode sound design was by Michael Simonelli and the Charts and Leisure team.
Thanks so much to Kenny Mers and Francesco Evangelista for joining us. We'll see you next time.